This video will discuss the energy levels and wave functions of the three-dimensional harmonic oscillator. So for the 3D harmonic oscillator, what we need to do is solve the Schrodinger equation just as we did in one dimension. So to do that, first we need to specify what our potential energy function is. So that'll be V of x, y, and z. So that'll be three parts, a potential in x, y, and z, 1/2 kx x squared, plus 1/2 ky y squared, plus 1/2 kz z squared. In each case, the spring constants are unique to the individual x, y, and z dimensions. So our Schrodinger equation, h psi equals E psi, is going to be our kinetic energy operator plus our potential energy operator acting on psi equals E times psi. So we have minus h bar squared over 2m. That can still be mu there for m. Of second partial derivative with respect to x plus second partial for y plus second partial for z. That total is the Laplacian operator, del squared, plus v of xyz times psi equals E psi. Luckily, we can do our favorite trick for partial differential equations. We can separate variables. This Hamiltonian is separable into a Hamiltonian of x, Hamiltonian of y, and Hamiltonian of z. So the Hamiltonian of each individual dimension, x, y, and z, is minus h bar squared over 2m, second partial with respect to I, plus vi of variable I being x, y, and z. So since the Hamiltonian is separable, that means the Schrodinger equation is separable into each dimension. Hi psi ni of I equals E ni times psi ni of I. And the energies of each of these individual dimensions is the energy of the one-dimensional harmonic oscillator model. H nu I times ni plus 1/2. Ni is some integer that starts at 0, goes up into infinity, and the angular frequency in that dimension is 1 over 2 pi times the square root of the spring constant in that dimension divided by the mass, and our mass here still would be a reduced mass. Okay, so our total energy is a function of three quantum numbers, nx, ny, and nz, and it is a sum of the energy of each of these individual dimensions, enx plus eny plus enz. All three of those being integers starting at 0. Our wave function then, in separation of variables, psi nx, ny, and z of x, y, z, is a product of the wave functions in each dimension. Remember, separation of variables means the wave functions are a product and the energies are a sum. So psi nx of x, psi ny of y, psi nz of z. All right, so we have some graphs over here. Let's assume that nu x equals nu naught, nu y equals twice that, and nu z equals 3 times that. So in units of E over h nu naught, the energy levels are going to be 1/2, 3/2, 5/2, 7/2, 9/2 for the EX. For EY, it's going to be 1, 3, 5, etc. And for EZ, it's going to be 3/2, 9/2, etc., going up from there. The density of states here depending on what the frequency, the angular frequency is in each of the individual dimensions, determined by their spring constants. So if we have the case where it's equal in all dimensions, kx equals ky equals kz equals some constant we'll just call k, then the total energy is just h nu, because they all have the same nu, having the same k, h nu times nx plus ny plus nz plus 3 times 1/2, because each of these has a 1/2 of their own. So it's 3/2 at the minimum, and then the sum of the three ends. So the energy over h nu naught, if they're all equal to nu naught in each dimension, we have 3/2, 5/2, 7/2, 9/2. But what we'll note here is that the symmetry, again, as in particle in a box in 3 dimensions, has caused a degeneracy. So E000 is 3/2. E100 in terms of nx and y and z is going to be 5 halves, but 010 and 001 are also 5 halves. So the degeneracy at 5 halves is 3-fold. The degeneracy is 6-fold at 7 halves and 10-fold at 9 halves. Because here this is all permutations where nx plus ny plus nz adds up to 2. Here this is all permutations where they add up to 3, and there's a quadratically increasing number of those permutations as we go up. So for a harmonic oscillator in multiple dimensions, any kind of symmetry very quickly leads to very high degeneracy as we go up higher in our energy levels.